What is engineering? By Lexi. Engineering, what is it? Many think they know what engineering is all about. I know I did. It's science, plain and simple. Interestingly enough, that isn't the case. Science deals with the natural, while engineering deals with the artificial. Engineering is the application of math and science in a practical way to improve the quality of others' lives. Engineers. Engineers have a slightly different definition. They utilize a series of problem-solving skills to build, design, and invent objects in order to aid humankind. This is considered to be the invisible or silent profession because engineers tend to be behind the scenes, creating the things we use every day. Engineering is the second largest profession in our nation. Over 2.1 million engineers are in the workforce of America. The disciplines of engineering. There are four major disciplines or areas in engineering. There's chemical engineering, there's civil engineering, there's electrical engineering, and finally there's mechanical engineering. Chemical engineering. A chemical engineer discovers and improves upon items that are chemically combined. This means they create new drugs and help improve crop yields for farmers. They also improve upon items like tennis shoes. For example, they might take the rubber of the shoe and make it to the consistency they want it to be. They often work in pharmaceutical, chemical, and petroleum companies. They are not limited to these. No engineer is. Civil engineering. Civil engineering is ranked number 10 in the highest paying profession by Money Magazine. This is one of the oldest and largest branches of engineering. The engineers in this branch create the infrastructure of our whole society. Literally. They take roads and make solutions for highway congestion. They take buildings and make them hurricane-proof. They remove designs from paper and make them a reality. Civil engineers often say that it's the architects that put designs on paper, but engineers actually get things built. Electrical engineering. Electrical engineers work in a field that is only 100 years old. These engineers design and work with electrical, electronic, and electromechanical devices, circuits, and systems. They take wires and magnets and figure out how to make something like a portable stereo operate without being cumbersome to carry. They craft it so that it becomes contemporary and easier to utilize. Every technological device has been designed, manufactured, and/or modified by an electrical engineer. This discipline of engineering draws from multiple other disciplines like chemistry, physics, and solid-state electronics. Mechanical engineering. Mechanical engineers take us from point A to point B. I don't mean just literally. They create almost anything that involves a mechanical process. The mere word mechanical engineer mostly brings to mind the picture of a car or engine. They do so much more than that. For instance, this type of engineer can build edifices underwater. To do this, they have to find a way to bring air into the building, as well as keep the inhabitants dry. The engineer also must keep the components of the structure from eroding or rusting once it is in the water. This is why mechanical engineers are often referred to as general practitioners. They work in nearly every area of technology. They are the ones who have invented toys, wheelchairs, and medical devices. Biomedical engineering. While there are only four main disciplines of engineering, there are hundreds, if not thousands, of specializations and extensions of these. Biomedical engineering is what I personally want to specialize in. Its core involves a combination of the disciplines of chemical and mechanical engineering, as well as electrical. But it is as different as it is similar to these. Though much of the technology created in biomedical engineering is chemically combined or electrically operated, biomedical engineering as a whole is almost worthy of its own discipline, especially since there are sub-specializations like biochemical, bioelectrical, and biomechanical engineering in this field. This means that a biomedical engineer may create synthetic blood vessels, which involve a chemical aspect, or advanced surgical devices like lasers, which involve a more electrical or mechanical aspect. Biomedical continued. These engineers solve intricate medical problems through engineering principles to aid the healthcare system. They develop technologies that will alleviate or treat biological or medical problems. As a biomedical engineer, one can go on to the medical school, law school, or teach. Medical schools tend to accept those with a biomedical engineering major over other majors. Water supply and distribution. Water was once a dangerous yet most desirous thing. There was hardly enough of it, and what little there was contaminated with diseases due to feces and chemicals. With this problem in mind, engineers began to use chlorine to eliminate the harmful germs that made water unsafe to drink. Engineers then worked on the root of the many diseases: waste. Sewage treatment plants were designed and erected to prevent the diseases. Aqueducts, reservoirs, dams, and storage tanks were then all created to make water more abundant in particular regions. Water supply and distribution continued. The engineers who had their hands deepest in this movement were probably the civil engineers. The definition of a civil engineer, according to the Discover Engineering website, is the art and science of designing the infrastructure of a modern civilized society. Infrastructure literally means the basic physical and organizational structures and facilities, e.g., buildings, roads, and power supplies, needed for the operation of a society. Therefore, one must conclude that aqueducts, sewage systems, and dams are all major parts of America's infrastructure. They were constructed by civil engineers. These things were also used to solve the water supply problem and were the most prevalent in doing so. So the civil engineers must have played the biggest part in water supply and distribution. Grand Challenge. A grand challenge is determined by the committee of the National Academy of Engineering. Health informatics is the grand challenge I would undertake. It coincides well with biomedical engineering since they both deal with medicine. This challenge is, in part, to maintain a healthy population in the 21st century by redesigning, inventing new technology, and creating a national, if not global, patient record system. Importance to a solution. Advancement in health informatics would lead to an altogether healthier society. Our world is a lot smaller than it was 100 years ago. One can fly from America to China in a little under 24 hours. If an epidemic were to break out, knowing the second it occurred would ensure the occurrence could be contained. Also, health informatics could save thousands of lives through the creation of new technology. There's a small wireless device embedded with transmitter receivers that can monitor a patient's vitals whether they were at home or in the hospital. It's a lot like Life Alert. With advancements made, every hospital room could be turned into a virtual ICU. There's also the less technical aspect. With a global record system, the health systems would be able to provide efficient care to patients without having to do a lot of sorting and digging. Currently, not every hospital has the same record system, which causes a lot of complications. Contributions. Biomedical engineers are well versed in medicine. They understand the human body and are able to do one of the most important things in health informatics. They're able to use technology to improve the quality and care. They're also able to create technologies that would detect pandemics and epidemics. So I, as a biomedical engineer, would have the ability and knowledge to construct a device that was implantable to the human body. It would read as a data chip and be made of materials that wouldn't harm the human body. This would be an efficient way to store the patient's information and continuously maintain their vitals. This kills two birds with one stone. The need for an international database is satisfied, as well as the need to continuously monitor the patient.